Hello. This lecture is intended to help us walk through the different concepts surrounding the use of fixed area plots in forest inventories, including things like correcting for the effects of slope on fixed area plot boundaries, and also how to do stand edge correction at the edges of stands for plots that fall on our perimeters. When it comes to using small fixed area plots, these plots can come in any shape that we can think of, including small rectangular plots, square plots, circular plots, any fixed area that we can use to delineate objects for inventory. When we set up fixed area plots, we are using these based on a probability proportional to frequency of the objects within the population. This means that small objects like these little trees that we have a lot of in this population will have a higher probability of being intercepted by these plots and counted within these plots than these larger, less frequent trees within this population. Additionally, when we use these small fixed area plots, we are looking to scale this data from the observation within an individual plot to what it would mean at the acre basis, and by using an expansion factor, and we'll talk about this more later. Fixed area plots can come in all different sizes and shapes depending on how we want to work with our data. Commonly, we'll see circular plots and square-sided plots. But it's also good to be comfortable moving between both English unit systems and metric systems within these approaches, as they're often used interchangeably in many different fields of natural resources. Although cheat sheets like the one on the previous slide are highly useful in setting up our plots, sometimes we get asked to use plot sizes that are kind of an abnormal size. So let's assume we are asked to install a 1/17 acre circular plot. How would we go about figuring out the radius of this plot for flat ground? We would start by wanting to know the area of a circle is equal to pi times the radius squared, and that when we have an acre, it is 43,560 square feet. And so to find the area of a 17th acre area, we have 43,560 square feet in an acre divided by 17 plots, tells us each plot would contain 2,562 square feet. With that in mind, we can set that equal to our pi r squared and then use algebra to solve this equation backwards. So we're going to divide pi across through both sides, giving us 815.6 equaling r squared, and back out that radical. So take the square root of 815.6, leaving us with a radius of 28.6 feet. Let's presume we're doing a similar inventory, but this time we're working in Canada and we're using 1/6 hectare circular plots. So again, to find that radius, we need to know that the area of a circle is equal to pi r squared, that the area of 1 hectare is equal to 10,000 square meters. So if we divide that by our 6 plots within that hectare, each plot will contain 1,666 square meters. If we set that equal to our pi r squared, we can start to solve this algebra backwards. So we divide that pi across, leaving us with r squared equals 530.5 square meters, and then back out that radical, we're left with a radius of 23 meters. Now let's talk about some of the advantages and potential limitations of different plot types. If we start thinking about things with right angles at their corners, such as squares and rectangular plots, they become very easy to determine if a tree is in or out by simply sighting down the boundary and determining is the midpoint of a tree inside or out of the plot we're dealing with. Additionally, rectangular plots can have a nice advantage when it comes to trying to capture the complexity of a forest across interacting topographic variables. So if we orient rectangular plots up and down the slope, they can capture across the gradient from high moisture content areas at the bottom or toe slope to low moisture content areas up at the ridge top on a slope, which helps us capture that variation within the individual plot itself. But at the same time, those rectangular plots can be hard to work with when those thin plots take a lot of time to inventory. It can lead us to only have the ability to sample a very low number of plots, potentially reducing the power of our analysis and the ability to detect differences. Here are some simple thoughts on how best we might go about setting up a rectangular plot. It's easy to set up some kind of reference corner to be working off of, and then pull one of our base directions along whatever compass bearing we need to have this pre-orientation for our lines, pull another one at 90 degrees, but then to make sure that we're maintaining a 90-degree angle in this corner, we can check the separation distance of those 2 points by taking the square root of 2 times the side length squared to make sure that we're setting up a nice right triangle here. And then we can flip those 2 tapes to have them meet and set up this last point on this corner. So as rectangular plots have their advantages, so do circular plots. Circular plots are incredibly easy to set up because all we need to know is the effective radius of the plot itself, and we can walk in a circle to start identifying the boundary itself. And having no predetermined orientation like a rectangular plot makes it really easy for this plot to be validated or check cruised by somebody else to ensure the quality of the data being collected. Because all they have to do is find the same central location and they can set up the same plot. Unfortunately though, these circular plots have more potential for errors at the boundary, and we will ultimately wind up seeing that these trees at the edges wind up having to be checked more often to make sure they're inside or out. Additionally, circular plots are harder to wind up correcting for slope, and we'll look at that in just a minute. Again, when it comes to setting up circular plots, the easiest route is to set up some kind of plot marker at the center of our location, and then most people will set up cardinal points in our cardinal directions to indicate the perimeter of our plot by just pulling tapes and putting some kind of a marker at the end of the radius in our 4 cardinal directions. This makes it easy to indicate that if we wanted to follow the inventory by starting from north and working our way in a clockwise direction, we could inventory all of the trees, and if we set that as our protocol, somebody else could follow the exact same system and inventory the same trees in the same order for validating our data. If we think about the structure of most natural forests in the world, we generally have a higher proportion of small trees compared to the density of larger mature trees within the system. This can pose problems sometimes for fixed area plots unless we really think through how to utilize the system well. In order to account for this ability, we need to think about how fixed area plots inventory objects in the natural world. And these operate by sampling trees based on the frequency they occur within our population, which is commonly referred to as probability proportional to frequency, meaning that these highly frequent small regenerating trees are more likely to be captured in any given plot than large trees. For just a second, think about how we might modify this design in order to help us capture more large trees within a fixed area plot. Although not always evident, we have the ability to sample different parts of the forest using slightly modified sampling designs, where we might wind up nesting multiple plots together in order to use different plot sizes to sample different sized trees. This helps us account for that issue of varying densities of these different sized trees within a forest. This means that for our largest, most mature trees, we might use a really large plot, like something like a 1/5 acre plot. Whereas some kind of intermediate pole-sized tree, we could use something like a 10th acre plot. And for our small regenerating trees, we could use something closer to a 1/100th acre plot, so that we're not counting these small trees forever on a 1/5 acre plot, but we're capturing enough large trees on this 5th acre plot to actually characterize what is happening in the population. A fantastic example of these nested plot designs is what is used by the U.S. Forest Service's Forest Inventory and Analysis Program, where they use these complex nested designs where there's multiple different subsampling units inside of the same population, where some of these are conducting small regeneration samples inside of here. Some of these are sampling the majority of overstory trees within this population, and then some of these are sampling all of the overstory large mature trees at the same location that might not show up at the smaller plot sizes. Another great example of this is the fire effects monitoring system, commonly utilized in post-fire monitoring, where in these plots we have multiple nested plot locations where we have things for 1/50th hectare circular plots for tree measurements, 1/100th hectare circular plots for shrub and sapling or small tree measurements, and then nested small plots of 750th hectare plots or a 2-meter radius plot for monitoring things like grasses and small forbs in the same location, so that we have these nested co-located data to understand what's happening in the system. Switching topics a little bit, when it comes to scaling fixed area plot data to represent a more useful scale of the data in terms of understanding what's happening at the per acre level, we can often take an individual plot, where these are 1/10th acre square plots, observe how many things were identified within that plot, and we multiply that by a simple expansion factor to understand how many things per acre this represents. Since this was a 1/10th acre plot, all we want to do is know that 10 of these fit into 1 acre, or we want to take the reciprocal of this 1/10th acre plot being 10 over 1, so we multiply the 4 trees in the plot times 10 to tell us that we'd have 40 trees per acre, making our expansion factor the 10. Now let's think through the calculations for calculating the number of trees per acre and the basal area per acre coming from an inventoried 1/20th acre plot. So if on this plot we inventoried these 3 trees of DBHs of 8.8, 10.2, and 12.4 inches, we could determine the trees per acre by taking the number of trees identified in the plot times the plot expansion factor to get an estimate of trees per acre. So for this plot, we're going to take our 3 trees in the plot times the reciprocal of our 1/20th acre, so 20, to tell us we have 60 trees per acre. Now if we wanted to work through this idea of calculating basal area per acre, we need to be able to get the individual tree basal area, sum the basal area within that one plot, and multiply it by our expansion factor to convert it to basal area per acre. So this means we can calculate the basal area of our first tree by taking dBH squared times 0.005454, and then do this for our second tree, and also do it for our third tree to get this term for our summation in here. So if we convert those numbers, we see that the first tree is 0.422 square feet, the second tree is 0.567 square feet, and the third tree is 0.839 square feet. Summed up times 20 would give us an estimate of 36.6 square feet per acre. An important thing to understand is that when installing fixed area plots or even variable radius plots on a slope, that slope has an effect on how we see the natural world. It changes our assumption of a horizontal distance dictating how much area we're actually sampling on the ground. So this means we need to adjust the length of our plot to account for the effect of slope, changing a circular plot from being a circle to being an ellipse going up and down the direction of the slope. So if we think about the effect of slope on a circle, this plot on a horizontal flat plane is a nice perfect circle. But if we project that down onto a sloping surface, this point hits first, and then it elongates that circle down the hill to produce an ellipse that we need to be able to account for in what it means for our inventory. So normally we know that our radius just equals pi r squared, but to get our new radius for what it should be going up and down the slope, we wind up taking the radius as the square root of area over pi divided by the cosine of the angle of the slope. So for a 1/10 acre plot on a 25-degree slope, we're saying that the plot area is 4,356 square feet divided by pi divided by the cosine of 45, giving us 40.1 feet, not the 37.2 feet that the radius would be going horizontally with the slope. If this had instead been a 25% slope, we would have to convert this 25% into the degrees it represents by taking the inverse tangent of 25 over the base distance for a percent of 100. This now would give us a new radius of 38.4 feet instead of 37.2 feet. There are plenty of situations in which it's really important to ensure we correct for slope and its effect on our plots. This is also true when using square and rectangular plots to make sure things are accurate. So we can do this for both circular plots, like the example we've already looked at, or this example here, or we can do it for square plots, where a 1/10 acre plot on a 33% slope would have 66 feet for the side length on the direction following the slope, but along the slope going up and down the hill, we would wind up modifying this slope to increase what the slope is doing to our radius, or to our side length. We can use common cheat sheets like this one here that's also available on the Canvas website to help us do this. So in this case, for our 33%, we find the slope category containing that number, tells us 1.05 is the modifier we want to use. So 66 times 1.05 gives us 69.3 feet going up and down the slope. To really make it clear why we care about making sure we account for these effects, if we work through a simple calculation exercise where we said we were inventorying 1/10 acre plots and we missed one tree on each of these plots because we failed to increase the radius to account for the effect of slope on the inventory, this would have at a 3% sampling intensity of the population of 75 acres. If we work this through, we would underestimate the volume on the site by 7,200 board feet. This has a potential value, if we assume $300 per MBF, which is the going rate for ponderosa pine, of over $2,000 loss. And this is assuming only missing one tree on each plot. That could be the difference between being able to pay for an operation like this or not. The next major component of dealing with plots within our inventories are figuring out how to deal with plots near the edge of our plot. These plots are incredibly important near the edge of our population, but at the same time, the trees existing on the edge of our population quite often can be different from what's happening in the center of our population, and therefore we need to account for them accurately so that we don't introduce any bias to our statistics. If we think about what's going on right at the edge of our population, these edge trees often could exhibit either less or more competition. Maybe they're growing along an edge and have no competition due to a road being there. Or maybe the edge is some kind of riparian area and they're growing faster because of improved growing conditions and having extra moisture available to them. We have a number of ways we could go about dealing with issues of plots that actually fall so that they straddle our stand boundaries. First option, although not great, we could simply ignore these plots and just deal with the data that collects with whole plots. This has potential to lead to bias in our representation of what's happening at the edge of these populations if we believe there's actually a difference between trees on the edge of the boundary versus those at the center of our population. Beyond this, we have several methods that can provide us a more representative way of sampling these edge trees. One of the simplest ways to deal with this then would be simply shift the plot so that the very edge of our plot falls directly along the boundary of the population itself. Ultimately, this is probably going to lead to a underrepresentation of the trees along the edge of our population and lead to a small bias in our calculations. Alternatively, we could do some math and actually augment the radius of our plots to account for the area being lost outside. Mathematically, this is a really great way to account for any bias effects that our inventory might cause, but conducting this math in the field to account for this area and increase our radius would not be simplistic to do, making it very difficult to execute well. Another potential solution that many people use is to do half plots, where instead of shifting our plot inside, we shift our plot so that we inventory 1/2 of the plot itself, and then ultimately we double count anything we observe inside of the plot as if we had seen everything twice to say that we have a whole plot. Ultimately, this leads to bias in the opposite direction and may overrepresent the things that are occurring at the edge of our population. Finally, one of my personal preferences is using something called a mirage plot or mirrored plot approach to trying to calculate what's going on at the edge of our populations. In this system, we have our plot set up and we have some component of the plot falling outside of the population. And so to account for that lost area, we fold that back in on itself and we double count anything falling within this smaller component of the population so that we can assume that we inventoried an entire plot. While this still can lead to some slight oversample bias of these edge trees, it is less bias than either shifting all the way in to have a whole plot or shifting to the edge to have a half plot, and is somewhat of an intermediate step for how to handle these situations. Finally, one of the preferred methods statistically that is becoming more popular as more forest inventory technology has the ability to record and handle some of these statistical calculations for us is that we can take partial plots, which means if we inventory, let's say, 80% of the area, we can weight these plots in our calculations and just keep track of the fact that this plot only counts as 80% of an entire plot. This should minimize any potential bias effects while giving us the most representative sample possible. Now we're going to talk about different ways these plots are commonly used. One approach using long, thin rectangular plots would be something called strip cruising, where we're passing parallel lines through our population, and often we want to orient these lines so that they're going up and down the hills. So if we think about these as the dominant riparian features within these watersheds, we could be passing lines of inventoried area over these to capture as much variation within these areas as possible. One nice feature of these things is it makes it really easy to determine the sampling intensity, or what is known as the proportion of inventoried area in the population, by simply saying if we have a strip or a plot that is 1 chain wide and we're traveling 5 chains between plots, we can just take a simple ratio of 1/5, telling us we sampled 20% of the entire population. These things have many great advantages to them using these long, thin rectangular plots, including the fact that we lose very little travel time between plots because we're so continuously sampling as we work our way along these rectangular strips. This is highly beneficial to production within these things, and we automatically get a representative sample of what's happening at the edge of these sites, since our plots all just run straight to the edge of our population. Unfortunately, these can also have some unintended issues, including making it very difficult to keep these plots straight and make it difficult for people to check cruise what is going on, as sometimes we're crossing very rugged terrain where we may have down timber, rocky outcroppings, making it difficult to keep straight lines passing through the woods. Alternatively, the other way smaller fixed area plots, including circles and squares, might be used is in what's considered a line plot cruising system, where we're doing some kind of systematic approach to installing a grid of these plots across the population. These plots can be used for a number of different inventory types, where depending on the type of data being collected, could be conducted by an individual person at each one of these. Additionally, since we're working on smaller fixed locations, we don't have as many issues about traveling through the natural world, as we can pass around obstacles to get to where we want to install the next point for our data collection. And additionally, there's one more analytical advantage that these can provide by enabling us to do what's called post-stratification of this data, where if we said all of these plots showed us very different species compositions than the rest of the plots, we could treat this then as its own stand, and then treat this as its own stand, and analyze the data separately in a stratified approach. Finally, when it comes to interpreting and using these systematic type approaches from these line plot systems, we can calculate the same idea of sampling intensity, where this time the intensity is going to be based on the area of our plot itself against the area each plot is representing. So that representative area of our plots is based on how far we travel between plots on a line, so in this case 4 chains, and between lines of plots, which is 5 chains in this situation. So 4 chains times 5 chains gives us 20 square chains, which is the same thing as 2 acres. So at that point, if we look and see that we're inventorying 1/5 acre plots, which is a 0.2 acre plot, divided by 2 acres, tells us we're sampling 10% of this population. Finally, we're going to talk about the role of monumenting plots so that they can be returned to within a forest inventory approach. This generally leads to us having 2 different strategies for inventorying trees. One in which we talk about having a stand-based inventory, and one in which we talk about having a continuous forest inventory. Within the stand-based inventory, we are often not intending to return to the exact same locations, because we're conducting intensive inventories in which we're going to use to plan a management action that will directly change the forest structure to the point that we don't care about doing direct change assessment. These continuous forest inventories, however, are often used for longer-term planning horizons and for other activities such as developing forest growth and yield models. As examples of these two strategies, if we look at the Idaho Department of Forest Land's approach to inventory, they use both stand-based inventories, where they're putting in one plot per 5 acres to help them make precise estimates of timber volume for informing timber harvest within the immediate future, whereas they're also utilizing continuous forest inventory plots that have been ongoing and in use by them since the 1950s, with these plots being used to help them ensure they have a sustainable harvest program across their landscape and to help them tune and develop growth models for modeling short-term management actions and the effect of future development at these sites. In order to utilize things like continuous forest inventories, we need to think through what we want to get out of them. Quite often, instead of having two sets of just randomly sampled plots, we have more power by monumenting and revisiting and doing direct assessment on a plot-by-plot basis of how each plot has changed through time. This can allow us to understand the direct effect of management on an activity, but is more time-intensive for establishing and remonitoring the exact same locations, as we have to be sure to mark and locate these same locations very readily. These inventory systems can be time intensive to conduct, as if you think about how Idaho Department of Forest Lands operates, they wind up putting in 3 horizontal bands on each of their trees and nailing a plaque to each of these trees on their continuing forest inventory plots, so they know exactly which tree is which, and this lower horizontal band identifies the height at which breast height is, so that the DBH can be collected at the exact same height every time this tree is visited. If we look at these two maps, we can see the difference in intensity of these two types of inventories because of what we want to get out of the data. In the CFI, we're looking at a much larger landscape in which there's just a handful of scattered plots, compared to the stand-based inventory approach, where we have delineated stand boundaries with fixed plots on a grid that's giving us very intensive data about this site.